This is section 6.2 on binomial probability distributions. This section's pretty long. It'll probably be broken into at least 2 videos, maybe 3. This is just a heavy section of the textbook, probably the longest one of the course. So give yourself plenty of time to practice this because it's not easy. So we have something called a binomial random variable, and you might have heard the term binomial before in your algebra class. Bi means 2. It's a prefix that means 2. And so a binomial random variable can only have 2 outcomes. So one of the outcomes is considered a success, and the other outcome is considered a failure. So there's one outcome you want, one outcome you do not want. So just a couple quick examples. If I'm flipping a coin, I might call heads a success, while I call tails a failure. And it could be the other way around, but one outcome is what you want, and the other one you do not want. If I'm rolling a die, I might say if I roll a 1, that's considered success. And I might say if I don't roll a 1, anything else is a failure. In the paper football example from section 6.1, we said making the field goal was considered success, and missing the field goal is a failure. So again, one outcome is considered what you want, a success. Everything else is considered a failure. So there's 4 criteria for a binomial probability distribution. The first criteria is that it has to be a fixed number of trials. I'm going to flick the football 5 times. I'm going to roll the die 10 times. I'm going to flip the coin 20 times. A fixed number of trials. Each trial needs to be independent. Same definition from chapter 5. The outcome of one trial does not affect the outcome of the next. Nothing's changing between the trials. For each trial, there needs to be 2 mutually exclusive outcomes. Another way to say that is disjoint outcomes. One outcome is considered success, the rest are considered failure, so mutually exclusive outcomes. And the last criteria is that the probability of success is the same for each trial. So there's 3 examples here, and for each one, we want to check all 4 criteria. So I'm going to number 1 through 4 for each example, and we'll check each criteria for all 3 examples. Okay, so for the first example, an experiment in which a basketball player who historically makes 80% of his free throws is asked to shoot 3 free throws, and the number of shots made is recorded. Alright, so we have this fixed probability. He normally makes 80% of his free throws. He's asked to shoot 3 times, so that is a fixed number of trials, 3. Each trial is independent. So whether he makes the shot or misses the shot, the probability remains the same. For each trial, there are 2 mutually exclusive outcomes. So success or failure is clear. You either make the shot or you miss the shot. So no gray area there. The ball either goes in the basket or it doesn't. And then the 4th condition, the probability of success is the same for each trial. So every time he shoots, he has an 80% chance of making it. They're not changing the basketball goal or changing the conditions or anything like that throughout the trials. So if all 4 conditions are true, it is a binomial probability distribution. Let's look at the second example. The number of people with blood type O negative based on a random sample of 10 people is recorded. According to the American Red Cross, 7% of people have type O negative blood. So the first condition is that there's a fixed number of trials. We said 10 people are being tested. Each trial is independent. One person's blood type does not change another person's blood type. And then we have clear success or failure when it comes to blood type O negative or failure. So it's one or the other. If it's O negative, it's a success. If it's anything else, it's a failure. And then the last one, does the percentage of success remain the same each time? Yes, we know there's a 7% chance each time for someone to have O negative blood. Generally speaking, if condition 2 is met, condition 4 will be met. If the trials are independent, then the probability generally remains the same. If condition 2 is not met, then condition 4 is generally not met. Let's look at the last one, a probability experiment in which 3 cards are drawn from a deck without replacement, and the number of aces is recorded. So there's a fixed number of trials. They're drawing 3 cards. Because they're not replacing the cards, each trial is not independent. We talked about this in Chapter 5. If I don't put the card back in the deck, all the probabilities have now changed. So if condition 2 is not met, you can stop there and say, no, this is not a binomial experiment. Let's continue just to make sure. There is clear success or failure. You either get an ace or it's not an ace. There's no overlap there. But because it's without replacement, the probability changes each time. So again, because condition 2 is not met, condition 4 will not be met either. So the first example was a probability distribution, the second one was, and the third one was not. So we're just going to focus on experiments that are binomial. So I think we're going to focus on example B for the next part of section 6.2. There's 3 letters we need to be familiar with for this: N, P, and X. We've seen N before. P and X are probably new for us. N is the number of trials. Number of trials. That's kind of like your sample size. P is the probability of success, and it's always as a decimal. And X is what I call the target value. Now, I'm not sure if your textbook calls it a target value, but I like that name for this. So it's the target value or the desired outcome. I like to think of it as a target value. So N, P, and X. And we're going to learn how to calculate different probabilities given the number of trials, the probability of success, and our target value. So your textbook goes through an example by hand, and then I'm going to show you how to put it all into the calculator. So we're going to use example B from page 3. According to the American Red Cross, 7% of people in the U.S. have blood type O negative. A simple random sample of size 4 is obtained, so we're just going to use 4 people for this, and the number of people with blood type O negative is recorded. Construct a probability distribution for the random variable X. So success, we're going to use the letter S, and that means you found someone with type O negative blood. Failure, we're going to use the letter F, and that means that they did not have O negative. They had any other kind, but not O negative. So if we survey 4 or test 4 people, if we test the first person, they might have O negative or they might not. Let's say they don't. If I test the second person, let's say they don't have type O negative. If I test the third person, let's say they don't, and the fourth person, let's say they don't either. That means we got 0 successes. So that's the probability of failing for all 4 people. None of them had type O negative. I could test the first person and they have type O negative, but then no one else does. That would be 1 success. I could test the first person and they don't have type O negative. The second person does, and the last 2 do not. That's another way of just having 1 success. The first 2 people I test could fail, the third one could be a success, and the last one could be a failure. That's another way to get 1 success. And then I could also fail on the first 3 tries and succeed with the fourth person having type O negative. So there are 4 different ways to have 1 success out of 4 people. And that's what's illustrated here. I could also have 2 successes. The first 2 people I test could be successful and the second 2 could be failures. That would be 2 successes. The first person could be a failure. The second person could be a success. The next person could be a success. And the last person could be a failure. That's another way to have 2 successes. Let's see, the first 2 people could fail and the last 2 people could be successful. That's also 2. The first and the last could be successful with failures in between. What else could happen? I could have success, failure, success, failure. That's another way to have 2. And I could have failure, success, failure, success. So there's actually 6 different ways, sampling 4 people, to have 2 successes. And that's what's illustrated in this row here. It's a little tedious. This should feel a little tedious. I'm not going to make you do this every time. I'm trying to prove a point here. So we have no successes, 1 success, 2 successes. I could have 3 successes and 1 failure. It could happen like this. It could happen on the second trial, could be a failure. The first trial could be a failure and everybody else could be a success. There's 4 different ways to have 3 successes, and then there's 1 way for all 4 to be a success. So there's actually 16 different possibilities when we test 4 people's blood types of whether they have O negative or not. And that's a lot. That's a lot of work to do. The moral of the story here is do not do this by hand. Your textbook goes into how to calculate all these different probabilities, and you have to add them all up, and it's a big old mess. The textbook also uses this formula that's in your formula book. You are more than welcome to teach yourself that formula. That's not something that I want to get into. That's more conditional probability, that's not part of the course. So I recommend letting the calculator do this work for you. This formula is interesting. I like it. And if it makes sense to you, that's awesome. Otherwise, let's just learn how to do this in the calculator. So I'm going to go straight to using the calculator to find the probabilities for particular values of x. So let's say I wanted to know the probability of getting 3 successes. So I wanted to figure out all of these and add them all up for the probability of getting 3 successes. So instead of doing all that by hand, the calculator can do this for us. You always put in N, P, and X. So the first number is the number of trials. In this example, it would be 4. The second value is the probability of success. You cannot spell today. Success. In this example, that was 0.07. And the third value is what we call the target value, which in this example is 3. So you just type in how many are in your trial, what is the probability of success, and how many do you want. The calculator will go through all the different combinations, and it will calculate all these probabilities and add them all up for you, and it just gives you that final answer. So let's go through these 4 practice problems using our calculator. Make sure that's in focus. The newer calculators are a little easier. The older ones, you have to remember the order. You're going to go to second and then vars, So let's see, let me clear this out. So you push second. Remember we talked about when you push second, the up arrow should appear. Vars is kind of below your arrows next to clear. Above the word vars is DISTR, which is distributions. So you're going to push second, vars. And you're going to go down, 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 down. And you should see binomial PDF and binomial CDF. Same thing on the older calculators. Down, down, down. You should see binomial PDF and binomial CDF. So right now we're going to choose option A, binomial PDF. Hopefully the glare is not too bad. On the newer calculators, it asks for the number of trials, the probability, and the x value. On the old calculators, you have to remember that order. So for example 17, our number of trials is 10. Our probability of success is 0.4, or you can type in 0.4, that works too. And our target value is 3. On the older calculators, you put 10, comma, which is right above the 7, 0.4, comma, 3. Let me make sure that's in focus here. You don't have to close the parentheses, but I like to close the parentheses. So on the newer calculator, you'll go down to paste. It will put it in for you, and then you'll hit enter. Older calculators, we just hit enter. And what that calculator's just done is think of all the combinations with 3 successes, use that probability of success, and added up all the possibilities to spit out your final answer. So, second vars, we did binomial PDF 10, comma, 0.4, comma, 3, and it spit out 0.21 if we rounded 50. This is very straightforward. When x equals a specific number, this is very easy. So binomial PDF, in this time is 15, probability of success is 0.85, and x is 12. So second vars, binomial PDF, and again the number of trials, comma, the probability of success always as a decimal, comma, and the number of successes you want. And the answer you're getting is the chance of that occurring. So this has about a 21.5% chance of occurring. This also has about 21% chance of occurring. So this is very simple. Binom PDF. Sample size is 40. Probability of success is 0.99, and I want 38 successes. So second vars, binomial PDF. Excuse me, 40, comma, 0.99, comma, 38. And you just record your number. Usually it wants 4 decimal places when you round. And the last one, second vars, binomial PDF, 50, comma, 0.02, comma, 3. So binom PDF 50, comma, 0.02, comma, 3. And I got 0.0607. Alright, same idea in an application problem. So 41% of all households are wireless-only households, which means they have no landline. In a random sample of 20 households, what is the probability that only one of them is wireless only? That's x equals 1. So we're going to do a binom PDF. Sample size is 20. Probability of success is 0.41. And I only want 1 success. So binom PDF 20, comma, 0.41, comma, 1. Now, on your calculator, you got that e to the -4, which means I'm going to move this over 4 times, which gives me 3 leading zeros. So my answer is 0.00036. And so for rounding to 4 decimal places, it's probably 0.0004. So be careful when you have that e to the negative whatever number. Move that decimal place over. It will not accept 3.63 because that doesn't make any sense. Alright, I'm going to change colors so you guys can continue to follow. So same setup, 41%, sample size 20. What is the probability that 5 of them are wireless only? So that's x equals 5. Binom PDF, 20.41 and 5. On the calculator, you can hit second and then enter. It'll pull up what you just typed in. You just change the 1 to a 5. So if everything's the same, just change that last number. We get 0.0656. And the last one, half of them are wireless only. Now half's a little tricky. They're not trying to be tricky, but they want you to think about if your sample size is 20, half would be 10. So in this case, x equals 10. We can't put in 0.5. That won't make any sense. Your first number and your last number have to be integers. It's just the middle number is a decimal. I hope the video does not cut me off before I finish the problem. Let's see. 20.41 and 10. Go ahead and type that in. And we get 0.1267. Alright, I'm going to stop there and I'll continue on page 5 in the next video.